Okay, today we'll be talking about bit shifting. So basically, you can either shift left or left shift, which is denoted by this symbol, or you're gonna right shift, which is usually denoted by this symbol. Okay, so let's say we had an int, which is 32 bits. Okay, and let's say we had the number 10, right? So the number 10 is 1, 0, 1, 0. Let's say we wanted to shift left one time. Basically, we're gonna shift the number left once. So this is gonna go here, this is gonna go here, this is gonna go here, this is gonna go here. So we're gonna get 0, 1, 0, 1. And then, but what do we fill here? Well, we're gonna fill that with just a 0. So now our new number is gonna be 20. 1, 2, 4, 8, 16. 16 plus 4 is 20. Now if you notice, we doubled our number. And that's because we went 1 up a power of 2. Meaning, we're going to multiply the number by 2. If we left shifted twice, we were going to go up by 2 powers of 2. So 2 times 2, which is 4. So we're going to have to multiply that by 4. So, let's say we had, so in this case, like in the computer science, like in the question, you'd have seen this as like, I don't know, 10 left shift 1. This is another fancy way of saying do 10 times 2 to the first power. When you're left shifting, you're going to multiply 2 to the nth power. You're going to multiply by 2 to the nth power, where n is the number of times you're going to shift. So if this was a 3, it would be 2 cubed, which would be 8, right? Now, what if we wanted to shift right? So let's say we had 10 again. 1, 0, 1, 0. To shift right, this would go here, this would go here, this would go here, and this would go here. So it would be 1, 0, 1, 0. And then you're going to fill this up with zeros. However, we're going to have 32 bits, and we shifted this guy to the right one time. So basically, this is getting thrown off a cliff. At least that's the way I like to think of it. Remember, this was your beginning bit. This is your ones place, your beginning bit. We're shifting it this side, right? Now this one is going to be your new one. So if, essentially, this 0 is removed. So if you're going to shift right 2 times, you're going to cross out the first 2 bits, and then fill the rest of these guys with zeros. So your answer is actually, so this was 10, this is now 5, right? 1, 2, 4, 1 plus 4 is 5. So if you notice, we actually divided by 2, or divided by, I'd say, 2 to the first power. So 10 right shift 1, essentially same thing as saying do 10 divided by 2 to the first power. So when you right shift, you're going to divide by 2 to the nth power, where again, n is the number of times you're going to shift. There is a thing called logical shift. So this is called arithmetic, and this is called logical. You might see these come up. Now, what arithmetic does is it preserves the sign. If it's negative, it's going to be negative. If it's positive, it's going to be positive. Logical doesn't preserve sign. Doesn't preserve sign. And we'll get more into that right now. I'm going to my example. So let's take a closer look at the difference between arithmetic right shift and logical right shift. So let's say we're going to do byte. So remember, 8 bits. Let's say we have the number -10. So 1, 2, 4, 8, 16, 32, 64, -128. 10 is 8 and 2. But to do 2's complement, we're basically gonna do, remember, it's a 1, 0, 1, 0. So this is gonna be a 1, 0, and everything else is gonna be a 1. Or you could have noticed that 128 minus 110, no, 128 minus 118 gives you 10. Whatever. Anyways, so beside the point. Let's say we're gonna right shift this, or arithmetic right shift this one time to the right. So our most significant bit is a 1, meaning the answer is negative, right? So because our most significant bit is a 1, whenever we shift to the right, so if we're gonna shift this to the right one time, right, we're basically gonna move these guys one place to the right over here. So we're just gonna remove the 0 and pretend that now this is 1, 2, 4, 8, 16, 32, 64, right? So shift to the right one time, we're gonna get 1, 1, 0, 1, 1, 1, 1. But what about this space right here? Do we fill that with the 0 with the 1? Well, because our most significant bit was a 1, we're gonna fill that up with a 1. Hence, the sign is preserved. Now this answer is -5. Let's say we're gonna arithmetic shift it, logical shift it, my bad, one time to the right. Well, it's gonna be the same answer, right? 1, 1, 1, 1, 0, 1, 1. Now what do I do with here? Well, with logical shifting, you're gonna put it with zeros. It's sometimes people call logical shift right shift filled with zeros. So let me write that down. Right shift filled with zeros. So that may be a good way to memorize what the 3 greater than signs do. You right shift and you fill up with zeros always. So now your answer is not gonna get cut in half. It's actually gonna be, in this case, 123. So sometimes when you see a logical shift, your answer is always gonna be positive, and it's gonna be a big number too. So if you see a big number, positive, and it's you had done logical right shift, then most of the time the big answer is gonna be your answer. Now if you arithmetic right shift it, which means it's just the 2 greater than signs, the sign is preserved, and you're just gonna cut it in half. But let me give you a summary before I get into what I just said earlier. So let me give you a quick summary. When you left shift, you don't have to worry about converting the number into binary. Just multiply number by 2 to the nth power. Always. Okay? Now you do have to be careful though. Sometimes they might give you, again, a byte, which is 8 bits. And they may ask you to shift it to the left, to the right, like n amount of times. And in there, you can't get past, like if you multiply the number when you left shift, your number can't exceed -128, right? Because a bit, the min it can get is 128. So sometimes you should convert the number into binary, but most of the time we're working with ints, at least in the multiple choice. So just multiply the number by 2 to the nth power. Now, when we do arithmetic right shift, which is the 2 greater than signs, sign is preserved, if the sign is positive, divide by 2, truncate the decimal if needed. If sign is negative, convert the number to binary and shift n times. You have to do this because if you divide by 2 and you truncate the decimal, you might be one off the actual answer, which most of the time that is what's happening. So if the sign is negative, convert to binary and shift. If you're doing logical shift right, then convert to binary, shift right n times, fill with zeros, and then yep, that's logical right shift. And yeah, that's pretty much it. Remember, 2 greater than sign is preserved. 3 greater than sign is not preserved. However, if they're both positive, like how do I say it? If your number that you want to shift to right is positive and you're doing logical right shift, it's going to be the same as arithmetic right shift, right? Because you're filling with zeros, and because the most significant bit is a 0, because the answer is positive, right? The 0, it has to be positive. Then it's going to be the same answer. But if your most significant bit is a 1, then logical right shift, you're still always going to fill with zeros. But your arithmetic right shift, you're going to fill with 1s to preserve that sign. Left shift doesn't matter because logical left shift and arithmetic left shift is the same thing. So you're just going to multiply by 2 to the nth power. Yep, that's it.